Hey friends, how are you? Hope you are doing well. So today we are going to learn about triple integration. You already know that triple integration is very much important from the IIT JAM perspective, as well as if you want to do advanced fees, then triple integration cannot be avoidable. You have to do the triple integration. So we are going to learn about triple integration. First of all, I'm going to introduce the concept of triple integration, and then I'm going to show you by doing an example. So let's get started. In the previous videos of mine, we have discussed about the double integration, in which we have talked about that in the Cartesian coordinate we have, let us say, dy dx or maybe dx dy. And I had also shown you that if you change the order, the result of the integral will not change. But what you are, you have to care about that how you're gonna put the integrals. So when I'm writing this integral for this dy and this integral for dx. So according to it, your y will be on this one as an x and this integral at dx. Now similarly for dx, this integral will be handled for dx and the limit will go for dx, and similarly for the dy. So that is the most crucial aspect of this double integration. We have also seen that we can transfer this dx and dy into the r d theta or dr. Okay, so this is called the polar angles. So in this video, we are talk about the triple integration, where our integral will have three integral, in which the integral will reach from dz to dy to dx. So by default, we are going to use this approach, in which you are going to first do the integral in z, and then we can do the integral in dy, and then again we can do the integral in dx. So how are we going to write? So whenever we do first dz, I'm going to write over here that whatever the limit you're going to put, let us say that you're going to put limit, and this limit will involve with fxy. Okay, so fxy. So when you are done with this limit, then you are going to have this dy, and in this dy, you will have this gx and let us say f1 and f2, g1x and g2x. Okay. So this is for dy, and now from here a to b, and there you go for the dx. So this is the way we are going to handle this triple integration. And when you do this triple integration, this will give you the result of the volume. So when we are doing this triple integration, for an example, suppose you have a sphere. So a sphere is a 3D region, okay, which is span over this three-dimensional space where you have x. So usually what we are going to write that when we are selecting the coordinate system, our coordinate system will look like that. This will be x. So the coordinate that is coming out of the screen is x. If you go inside this one, which is minus x, go right, you will have y, and going left, it would be minus y. And if you go above, it is plus z, and going downwards is minus z. So this is the kind of a coordinate system in which we are talking about, that this one is x, this is y, and this is the z. So we are no longer in the space of x and y. So we are not adopting this kind of thing, the x, y, and z. Okay, so we are going to work out x, y, and z. So this is kind of mathematically good, and you will see that why it is too much important. Although it is no importance of from the result perspective, there is nothing, just adaptation of standard mathematics. So you have certain kind of space. For an example, in 3D dimensional space, you have structures like cylinder, okay, maybe cone, maybe some abstract functions, let us say x, y, and z, which is defining some kind of region. For an example, you have some kind of torus, which is some particular height as well as the area and so on. So you can find out the volume of some certain thing. So whatever the space, and if you want to find the volume of it, you have to take an integration of the complete volume. And usually what we can do, whenever we say some things, like you can say that okay, there is something we can cut out, and this cutting is kind of cuboid, and you can think of it as a cuboid. Okay, so if you are going in this direction, x, y, and z direction, so what you can say that if you are coming this side, you have dx, you're going this way, it is dy, and when you're going upwards, then it has dz. Okay, so the volume can be find out just by taking the integral in terms of dz, dy, and dx. Okay, so this is the way we can do. So whenever we try to find out the triple integration of any particular function, so what we're going to do, first I'm going to make a region where this is x, y, and z. So for an example, when you are looking at the sphere, so what you see, the sphere is made up of circles and so on. So x square plus y square is equal to r square is the parametric equation of circle. But when you are writing the sphere, you have to add one more thing: x square plus y square plus z square is equal to r square. Correct? So it means that you have some circle, and these circles, when your radius is varying, then you will have something like sphere. Correct? So this is how things can be written. So now it means that the base of the circle, if you are cutting any sphere, the base is always a circle. For an example, here also you can see that for the cylinder, the base is circle. On the other hand, you have the cone. Cone is also, the base is also circle. So it's in a very special case. I'm not saying it that the base has to be circle. So in some sense, that they have 2D surface, 2D structure over here, and there is a length, and there is 1D. So addition of 2D plus 1D has made this 3D. So whenever you try to visualize anything, for example, anything in an object, so what you can say that suppose any object is over here. So over here, it means that at some distance, which is from perpendicular to y, this is the perpendicular axis from here. And then similarly, you have to take something, let us say that some shadow over here, you can say like this. Okay. So this is parallel to x-axis. This is parallel to y-axis, and when you go like upstairs, then you can say that okay, this is how much in the z. So if you are going in z direction, okay. So you can say that if some object is over here, how much it is in x. So the shadow of this object is over here. So I can particularly say that okay, this much in x, this much in y. So this much in y, which is perpendicular parallel to y-axis, this much in x, and this much in z-axis. So this has become. So this is how we can find the coordinate of any object in three-dimensional space. And this is the basic method to locate anything. Now, when we are trying to find the integral of any particular object in three-dimensional space, what you can do is, let me just again draw this thing. So for an example, there is something. Okay, there is some object over here. You can take, I have taken a shadow. So what I can do, I can take a point over here. And first of all, I am just starting from dz. Dz means that the integration which is going in z direction. So first you have to choose that, okay, this is the z plane. So how much this z, what is the shadow along z axis, which is parallel to z axis. So let us say this is z. So for an example, what I can show over here, that let us say that the z limit, because see that this is in the xy plane, and z, whenever you will choose z, let us say this is in this are the z. So you have to, what you have to require is you just make one line over here, so which is parallel to z axis. This is like, this line is parallel to z axis. So this is going from down to upstairs, and whenever you going from down to upstairs, it will cut two surfaces. For an example, it is cutting over here and over here. So let us say this is f1, which is again depending on xy, and this point will depend cutting on f2 xy. So this is corresponding to z2, and this is corresponding to z1. So I can say that okay, the limit would like be f1 xy, and over here f2 xy. Now when this one is done, now you are in xy plane. So you are seeing the shadow of any three-dimensional object. Now over here you have to take an integral of dy. So how will you put an integral of dy? So you have to just take one particular line which is parallel to y-axis. So at fixed x, you can just say that okay, this is something you are taking it. So you can see that it is cutting this line, this region from here to here. So when you're going from left to right, So you have to see that initially what it has, cut the point, and finally it is cutting the point. So I can write in terms of y1 is equal to, let us say, x1, or y2 is equal to x2. So I can say that it is maybe g1 of x and g2 of x. So this is the second limit on the dy. And when you are finally done, then you have to take the limit in the x direction, which is parallel to this one. So this is the point at which you have to take a limit which is parallel to x-axis, and this is coming from, so from here to here you have to always mind it that it will come towards you, means that it is coming from negative x-axis to a positive y-axis. So this will be, let us say, x1, and this would be, let us say, x2. So corresponding to it, let us say this is a and b. So I can say that this is the lower limit a and this is the upper limit b, and you have the integral b. So in some sense, I can just write that if you want to trace a volume of any particular object, I can simply write this as dz, dy, and dx. Dz would be like f1, which will be function of x1, x comma y. Over here, it will be x comma y. Dy would be g1 comma x and g2 comma x, and dx will be some, just a and b, some particular coordinate, and you have the scalar quantity, that what is the volume of any particular object. So using this, we can find just a very simple example. Let us say we have cube. Okay, so cube is a three-dimensional object. The volume would be dz, dy, and dx. Now in this cube, what happens is that your x, y, and z, everyone is perpendicular. So for an example, this is your x, this is your y, and this one is z. So each and everything is perpendicular, and we are considering that, okay, this is your 0 and this is going from 1, 0 to 1 and 0 to 1. So since everything is perpendicular, it is just manifesting the coordinate itself, means that this is the Cartesian coordinate itself. Okay, so z will go from 0 to 1, y will go from 0 to 1, and x will go from 0 to 1. So when you do this, then you will say that, so we can take this anywhere, like dx, then dy, and dz. Everything is independent of each other. 0 to 1, let us say 0 to 1. Okay, 0 to a, let us say, you can consider 0 to a, and so on. So you see this one is a, and which is giving you a cube. So this is how we can find out the volume of the cube, and there are much more complicated things we can extract it out. So whenever you can see that if you have these coordinates are mutually perpendicular or orthogonal, means that they are perpendicular to each other, then you don't have to worry about anything. You can just say that, okay, we can easily find it out. But you have the cases where things things can go south, means that everything is depending on each other, and you have to find out what could be the limit. So the thing is that everything is focusing on the limits. So in general, your volume can be depending on like this. And I have left one more important thing, that over here you must have some kind of function. Like, let us say, for an example, you have some particular structure which is constrained by some particular region. Then you can always find the volume of that thing at some particular in some particular limit or some particular constraint. Okay, so for an example, I'm just taking one example, which is again a simple one, but I think complicated. So for an example, let S be the sphere of radius 5 centered at the origin. For an example, you have a sphere whose radius is 5. So S is a sphere of radius 5 centimeter. Okay. And let D be the region under the sphere that lies above the plane Z3. So for an example, you can make a sphere look like it, and it is at Z is equal to 3. Okay, it is Z is equal to 3. So you can say that the sphere, let D be the region under the sphere that lies above the plane. Okay, so here they have said that, because suppose this is an sphere, what you can say that this is Z is equal to 3, or let us say that this may be Z is equal to 3. Okay, this is Z is equal to 3, which is under the sphere. Okay, So what you are required to do is that set up the limits for integration for evaluating the triple integral of any function x, y, z over region D. So you have to find the integral of this function fx yz over this particular region. That, this is a sphere of radius 5 centimeter, and the some plane is at z is equal to 3. So there will be some kind of particular region. Okay, so there may be some some function which is constrained in this region. So you have to find the volume of this particular function. So I'm going to use this triple integral, and we need to find dz into dy into dx. Okay, so how we are going to evaluate this thing? So you see that what is the parametric equation of a sphere? This parametric equation of a sphere is just like this: x square plus y square plus z square. Sorry, this is the radius square, so it has to be 5 square. And there is a limit, there is a point z is equal to 3, above which we are interested in some particular d region. Okay, so what we can do, first of all, I can just say that, okay, I have to take an integral which is like this. And since I am just doing the integral in this region, which is in this function which is constrained in this particular t, so my lower limit would be z is equal to 3, and then at this point, and we don't know anything about it, where it will lead us. So what I can get from here, that okay, I am just writing this one. Let us say I have dz. So dz is going from where to where? 3. And since this point is also on the sphere, then it must satisfy this equation: x square plus y square plus z square is equal to 25. So what I can write is that z is equal to 25 minus x square minus y square. Okay, this is the upper limit, because upper limit is because this function is constrained over this region, means that this function is not outside this region. It means that this function must be satisfied this one. So the upper limit would be 25 minus x square minus y square. Got it? So this is done. Now what happens? Now we have to take about this dy region. And when we are talking about dy region, it means that we have to take a parallel to y. So this is your y. So when you are seeing the y-axis, the problem is that when you are seeing the sphere, so the sphere have the base is kind of circle. Okay, so let us say this one is y and this one is x. So you see that when your z is equal to 3 done, because now you are seeing that at z is equal to 3, z is equal to 3, it has base, and this base is of a circular type. So again, I have x square plus y square plus z square is equal to 25. I can just say that x square plus y square at z is equal to 3 will be 9, 25. So I can say that x square plus, so I can just write that y square is equal to 16 minus x square, which is, so I can simply say that y becomes plus minus square root of 16 minus x square. Now you can see that when you are drawing the circle, it means that it is spanning from minus y to y. So when you are tracing a line, it will go from minus this one to plus this one. So I am just writing over here minus of 16 minus x square and plus of 16 plus x square. So now what you can say that, okay, I have a circle, and how can I know the x and y? So we already know that what is the equation of circle? X square plus y square is equal to 16. So that is already given. So once we have already deal with that, y is equal to this one and this one. So circle has the radius constant. So what is left is the radius. Okay. So we have already seen that this is spanning from this one. So we have already written this thing as this one. So I can just write it. Okay, this will go from minus 4 to 4, because just remove y and you will have plus minus 4. So this is spanning from minus 4 to plus 4. So this is how we can take the integral. We are writing the integral of any function which is constrained at z is equal to 3 and so on. So I hope you understand. So what we have done over here, that first we have drawn a sphere, and this sphere is spanning over the z axis x and y and z, and there is a plane z is equal to 3 which is inside the sphere. So z is equal to 3 is inside the sphere. Okay, now you have to take integral from z is equal to 3 to upper side. So whatever the function that we are constraining, this is constrained inside the sphere. So one point at z is equal to 3, then another point must lie on the surface of the sphere. So that is how we can just write that z is equal to 25 minus x square minus y square, where 25 is the radius square of the sphere. And then secondly, that we know that base of a sphere is particularly a circle. So just, at z is equal to 3, what is the circle equation? X square plus y square is 16. So I can just write y is equal to 16 minus x square. And since circle is a symmetric object, so whatever the y will be x. So y have been written in terms of x, and the left portion is that x square is equal to 16, and which is x will give you minus 4 to plus 4. Since it is spanning over the entire region, that's why we are doing it from minus 4 to 4. So this is how we can easily find out the volume. So I hope this much is clear to you. And in the next video, we are going to learn more about it. Okay. So before we are going to finish it, I'm giving you one more important thing, that how we can find the average, because these are just a concept. And in the later on video, we are going to do more problems. So average of any function, average of a function in 3D. So how we can find, let us say that I have a function which is f. I want to find the average of this function in 3-dimensional space. So what I can do is that, okay, this function is spanning over some volume of the region. Let us say the region is called D, and I can just take the triple integration. I can just write f into dv. And this particular thing is very much important when you are dealing with any kind of problem in quantum mechanics and so on, because there are a lot of averaging things. Because you can see that suppose an electron is in the region of circle, because you already understand hydrogen atom. Hydrogen atom is, you can treat hydrogen atom as a spherical one, and electron can be anywhere in this circle of radius. Okay. So the problem is that, what is the probability, or what could be the distribution of, what is the position of x, or maybe what is the momentum. So in that case, you have to first find out that what is the volume of the sphere, and then you have the x coordinate, and then you are trying to find that what is the expectation value of x. So this expectation value is nothing but an average value of x. So you cannot locate the exact location of electron. What you can just locate that, okay, what could be the average value of electron, average position of electron in the particular vicinity. Okay, so this is how we can easily find out. Okay, so there are much more examples and much more problems, so we can deal with in the later on video, and where we are going to also understand that how we can go from x, y, comma z to r, theta, and comma phi, which is called the spherical polar coordinate. Spherical polar coordinate. In the later on, we are also understanding that how we can find the volume of the circle by transferring it r, theta, and in terms of z. Okay, where z is the, this is the cylinder, and these base are what you call the circular, and just you are adding up all the circles like this, and you will get the volume of the cylinder. So I hope this is good, and we are going to do much more application of like center of mass, how to find the center of mass using the volume integral, how to calculate the moment of inertia, and so on. So a lot of the things are there, and we will just calculate one by one. Thank you very much. This is Saddam Cap signing out.